For number one, the first thing I want you to do is see if you can list the 4 types of motion. So go ahead and pause the video and give that a try. Okay, so the 4 types of motion are projectile, straight line, circular, and vibrational. I left some spaces because I have to give an example of each. So I've listed the 4 types, now I need to give an example. So a projectile, I'm going to let you choose your examples from the videos. So I'm going to give kind of a definition of each one. So you don't write down what I'm writing down, you write down your example. Okay, so a projectile is anything that goes through the air and kind of an arc shape. Okay, I always, it's kind of gross, but the way I always remember this is projectile vomiting. And that would make an arc, if that's some type of person, I don't know. But projectile vomiting, it comes out of the mouth. So straight line is anything that moves in a straight line. So maybe if you're thinking about something going down the highway, like a car, and it's going in a straight line. Circular, pretty much how it sounds, it's anything that goes around in a circle. And then vibrational can be anything that vibrates. So it could be you talking, it could be, a lot of you guys mess with your cell phones all day, so that's my cell phone vibrating. Okay, so there's a phone vibrating, it could be talking, anything like that. Okay, so now I want you guys to find examples from the video.
Get off my swing! Out of all the swings, he picks mine.
Uh-oh, here comes the kids. I'm going to leave this out on the court so that way they have to pick it up. Okay, so I'm going to pick a pretty easy example. For reference point, how do I know an object is moving? So if there's a tree, and then there's a ball, and then later in the video the ball moves. Okay, so now here's like an after. Now the ball's over here. So my reference point is going to be the tree. And how do I know the object is moving? I'd say the ball is moving because it's getting further away from the tree, which is my reference point. So you could say the ball changed position relative to the reference point.
Okay, so the tree, which equals my reference.
Whenever I don't know how to spell something, I just go up in the sentence and look for it. Because when I type this, it gives me the red squiggle, so everything's spelled right, most of the time. So if you don't know how to spell something, look up there in the question and see if you can find out how to spell it correctly. Miss Cox found the nearest spa and found out it was 50 kilometers away. She loaded up Pumpkin, her cat,
And took him to the spa because he was having a rough day.
Meow.
If her drive time was 10 minutes, on average, how fast was she going?
So the first thing I'm going to do is write down my speed, time, and distance. So the question asks, how fast was she going? So the speed is going to be our question mark. The distance is 50 kilometers. I know that I can tell that because of the units. And then our time is 10 minutes. So to find our speed, I need to use my equation. So I'm going to draw my magic triangle. I'm looking for speed, so I know that I need to do distance divided by time. So speed equals distance divided by time. I know my distance is 50 kilometers. My time is 10 minutes. So if I take these two and divide them, 50 divided by 10 is 5. And then my units, I'm just going to take kilometers divided by minutes. So it's going to be kilometers per minute. And that's my answer. on this graph, I want you to go ahead and read through the story, and then try to graph it on your own on this graph over here. So go ahead and pause the video and do that first. Okay, now that you've already tried yours, we're going to do this together. So the first thing I'm going to do is label my axi. So I'm going to write time. It goes on the bottom, and it looks like it's measured in minutes. And I'm going to write distance on the side. And it is measured in kilometers. Go ahead and write a title. You always write the effect of, and then whatever's on your x-axis, so your IV. And then on, and then your DV. So now I need to figure out how big my numbers need to be. So I know she's driving, and she went 4 kilometers. I'm going to write down 4 kilometers. And then she stopped, so she's not moving anywhere. Charlie came, freaked Miss Taylor out, and she made it the last 20 kilometers to school. So I know she went a total of 24 kilometers. And then she drove 24 kilometers back, so that's backwards, so I don't need to worry about that. And then she came back to school, which is another 24 kilometers. So I know that 24 is my biggest distance. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 lines. So I need to go up to 24, so I'm going to go up by 2s. Okay, so now I need to look at my time. So time just keeps going. It doesn't go backwards. So I just need to add up all my time. So I've got 5 minutes plus 3 minutes, 2 minutes, 5 minutes, and 10 minutes, 4 minutes, and then 14 minutes. Okay, so now I'm going to add all of those together. So that's 18, 28, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43. So I've got to get up to 43 minutes on the x-axis. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I've got 15 lines. So I could go up by 3s. I think I'll just go up by 5s. Yep, so now I'm ready to graph. So this is the part where I actually read through the story and see what happens. So Miss Taylor was driving a Camaro. She had driven 4 kilometers in 5 minutes. So I know she went 4 kilometers in 5 minutes. Now I'm going to go ahead and start at the 0. We're going to say, I'm guessing she starts at her house. Okay, and that's where the timer also starts. So her house is the starting point. And then she starts at 0 minutes. So I'm going to go ahead and connect those lines, or those dots. Then she saw a giant rabbit. She stopped for 3 minutes and stared at him. So now she's not moving. Her distance isn't increasing, but it's not decreasing. It's just staying the same. So it's going to be a flat line. She does that for 3 minutes. So that'll be 5, and now she's going to 8. 5 plus 3 is 8, so I'm going to draw a flat line. Then he hopped over the door into her front seat. He said, "Hi, my name is Charlie." This freaked Miss Taylor out, and she slammed on the gas. She made it the last 20 kilometers to school in only 2 minutes. So I know that she's at 4 kilometers, and she's going to go 20 more. So now she's going up to 24 kilometers, and it only takes her 2 minutes. So she was at 8, and now she's at 10. So 10 is right here. We're going to go up to 24, because it's 20 kilometers from here up to that line. Okay, so she's moving pretty quick because that line is really vertical. When she got to school, she sat in the parking lot for 5 minutes. So now she's not moving again. And we know 5 minutes, so she's going to stay at 24 kilometers because she's 24 kilometers away from her house. And she stays there for 5 minutes. She decided Charlie would make a cool classroom pet. She drove 24 kilometers back to her house in 10 minutes. So now she's going to go back 24 kilometers. So she's going to go all the way back down to 0. Right now she's at 15, and it takes her 10 minutes, so she's going to go down to the 25. So then I'll connect those dots. Okay, 10 minutes. She got, and to get a cage and some vegetables. She went to her house for 4 minutes. So that's going to be 4 minutes, so that's going to be a little bit before 30. So right there, it's going to be a flat line. Then she drove back to school in 14 minutes. Well, it doesn't say how far it is, but we know that she was already at the school once, and that was 24 kilometers away. So I'm going to draw a line in 14 minutes and back up to 24. So 14 minutes, so 5, 10, and then so 14 would be about right there, up to the 24. And then connect the dots. Yeah, almost. And so this is a graph of Miss Taylor's journey. I'm trying to connect that better. There we go. So now compare your graph to this graph. You probably did a lot better job.
Instantaneous speed is over the speed over just a very short amount of time, where average speed is the speed over a very long period of time. So I'd write in another way to think of average speed is total distance divided by total time.
Alright, so the next question is, what was Miss Taylor's average speed from the time she left her house until she got to school the first time?
So we want to know speed. So speed, time, and distance. So her speed is what we're looking for. Her time, well, let's see, it took her 5 minutes plus 3 minutes. She was staring at that rabbit. And then she made it to school in 2 more minutes. So 5 plus 3 is 8 plus 2 is 10. So we know our time is 10 minutes. And she made it to school, so we know that that's 24 kilometers. So she drove 4 kilometers, then stopped, looked at the rabbit, and then she made it the last 20 kilometers to school. So we need to find our equation. So I'm going to cover up speed. So distance divided by time. So now I've got 24 kilometers divided by 10 minutes. So that's 2.4 kilometers per minute. So this is her average speed, because I took the total distance divided by the total time. But now we want to know her instantaneous speed when she was freaked out by the bunny. So when she was freaked out by the bunny, she drove 20 kilometers in only 2 minutes. So 2 minutes is my time, and 20 kilometers is my distance. So magic triangle. Cover up speed, so distance divided by time. So I've got 20 kilometers, and it only took her 2 minutes. So that means she was going 10 kilometers per minute. So you can see how it was during the same trip, but her average speed and her instantaneous speed were different. So this is her average over the entire time, even when she was going 0. She was just sitting there staring at a rabbit. But then when she was freaked out, she went really fast, and so her instantaneous speed during that time was faster than her average speed. From a distance time graph, you can also get an idea of instantaneous versus average speed. So if I start off fast and then go slow, you can see that on the graph. But I could also just go the same speed the whole time and end up at the same distance away in the same amount of time. So that's the difference between, you can also see instantaneous, so I know I was going fast and then slow, versus average, which would be the same speed the entire time. Okay, so the definition of velocity is speed and a direction. So the speed, you can calculate it, just like we have with Miss Taylor's driving. But the direction, you could say north or south, or any of those, southwest, or you could also say away from her house. So you can use a reference point and say which way she's moving. So you could say away from her house, towards the school, or something like that. So you can also use reference points to say which way she's going.
Miss Walter really needs to go. She has a class, so she holds it. By the time class is over, she's not sure if she can make it the 4.5 meters to the bathroom. She does the pee-pee dance to the restroom.
Luckily, she makes it, and it only takes her 25 seconds to get to the restroom. We want to know what is her velocity. So to know velocity, I want 2 things, speed and direction. So first thing I'm going to do is calculate her speed. So speed is what we're looking for. I know the time is 25 seconds. And then 4.5 meters. So I need to find my equation. Still looking for speed, so I cover that. So distance divided by time. So my distance is 4.5 divided by 25 seconds. So now, let's see, I don't know what that is. So I'm going to get out my calculator and type that in. 0.18. So 0.18. And then I've got meters divided by seconds. So this is going to be meters per second. So I know that's my speed. And then I also need to know direction. So I don't know which direction the bathroom is. Is it north, west? I don't know. So I know her speed, so I'm going to say she's going towards the restroom. So I'm going to say 0.18 meters per second towards the restroom. I'm assuming she's using the one closest to her classroom, so if you want to put a direction, it would be east. But if you don't know the direction, then you could just use a reference point. So 0.18 meters per second towards the reference room. The restroom.
This motion sensor right here is my reference point. This is what's being used to measure the graph. So this graph is going to measure how far away I am from this motion sensor. So if the distance is increasing from the motion sensor, then my distance goes up. I'm getting further away from my reference point. Now I'm not moving, and so the line is straight. Now if I decrease my distance, I get closer to the motion sensor, then the line goes down because my distance is decreasing. So closer, the line goes down. Further away, the line goes up. Okay, so on a graph, if you move really slow, then the line won't have a very steep slope. But if you move faster, then you're covering the same distance, but in a shorter amount of time. So on the x-axis, this is going to be smaller, and then it'll be the same on the y-axis on your distance. So I'll see if I can make this one go faster. You can see how the slope is steeper, and I went actually a little bit further. The same amount of distance, but I took a shorter amount of time. So on this part, I took probably about 7 seconds, where on this one, I only took about 2 seconds. So that's why this one's faster. So the speed, I covered the same distance, but this one took less time. So if you do something in less time, then you do it faster. So we know the slope of the graph is the speed of the object moving. But on these graphs, it can also tell us velocity. It can tell us if we're moving towards the reference point or away. So right now my velocity is pretty slow, so that's my speed. And then I'm going away from the reference point. So that's speed and direction. So now I can go faster, and my direction would be towards the motion sensor, towards my reference point. So I'm stopped. So fast away from the reference point. So now I'm going slow towards the reference point. So you can tell on this graph, the slow parts are less steep, and then the fast parts are the really steep. So you notice I didn't go uphill or downhill, okay, to make this graph, but this is the distance. So this is how far away I am, and I did it in a short amount of time. So a short amount of seconds down here. So that's why it's real vertical. And then over here I did the close to the same distance, but I did it in a longer period of time, so that means this one's slower.
Okay, for this one, we're going to sketch a graph of the following story. So I want you to go ahead and read through the story, and then you sketch your graph right here, and you're going to try it beforehand. And then I'm going to sketch a graph over here, and then we can compare. So remember, you're sketching, and this story has no numbers in it. So all I want you to do is label your axis over here, and then just kind of sketch it. So there's not going to be any numbers. You're just kind of, what's the general shape? of this graph going to be? So go ahead and pause the video and give that a try. Alright, so now that you've tried, on a distance time graph, I'm always going to put time on the bottom. And then I'm going to put distance on the side.
Okay, so now I'm going to read through the story and get kind of an idea of what my graph should look like. So Miss Stansel is riding Hoof-Hearted, the horse. She started off galloping, which is fast. So I know that my line, I'm going to kind of do just a little sketch right here. So I know my line should go up, and it's going to be pretty steep because she's going fast. So they start off in a gallop across an open flower meadow.
Up ahead, they see a small stream. Miss Stansel slows the horse down to a walk and approaches the stream.
So I know this one's going to be a slower one, so my graph should be something a little less steep. And then they stop at the stream. So I know that should be a flat line.
And Hoof-Hearted bends over to take a drink. Miss Stansel wonders what that smell is and realizes it's a wildflower, so she rides back into the field, into the sunset, which is at a canter, which is between a walk and a gallop.
So now she's going back to where she started. So I know the line's going to go down, but it's not going to be, it's going to be steeper than the walk line, but faster than that one. So something kind of like that. Okay, so that's my practice graph. So now I'm going to draw one on the axis. So I know she starts off fast galloping. So it's going to be pretty steep. And then she slows down as they approach the stream. Notice the distance is still increasing, just not as fast. The line isn't as steep. And then they stop for a little while. And then she rides back kind of in between these two. So it's going to be less steep than that one, but more steep than that one. So maybe something kind of like this. So that's my graph for Miss Stansel's trip to the creek with Hoof-Hearted.